So let's look at what blood flow looks like through circulation. We've talked about the factors that influence flow and that going through the entire circulation matters for thinking about pressure. It's also going to matter for other factors that are really relevant for exchange across tissues, so at the capillaries. So let's graph these various factors here. So vessel diameter, blood pressure, cross-sectional area, and velocity of blood flow across circulation. Your book has these same images and it's a nice color coding with red and blue. I'm not going to try to do that, so I'm just going to do this in green. You already know what this will look like to graph vessel diameter over circulation. I'm going to kind of do an estimate. It might not be perfect in terms of what sizes are. Do my best here. So we're going to start large. We're going to get really, really small. And then we're going to get larger again, almost as large as before, right? We did that when we talked about blood vessels, these different types of blood vessels. We did this. This is another way to look at that same data. You should be able to match this up with that table that I drew and have both things make sense. They're telling you the same thing. You also may already know about pressure changes across circulation. You know it starts high. And average blood pressure, again, I'll come back to this. This is the mean. It's going to be about 100. That's partway in between our systolic and diastolic. That's what I'll tell you for now. It's one value that's going to represent blood pressure. Right. I think you're probably okay with talking about just pressure is going to decrease throughout circulation. So that's going to look like this. And it's going to continue to decrease throughout circulation. That drop might be a bit steep there. I didn't really mean to have like a super fast drop at capillaries. It's not linear though. It's kind of a little bit of an S curve. It drops throughout circulation. What happens to cross-sectional area? What do I mean by that? The total area that the blood is flowing through. That's a little different than, it's partly dependent on diameter, but it's also dependent on the number of tubes that you have, right? That's what area is going to be, both diameter and number of tubes. So we are going to have some baseline area, and actually it's going to go way up at the capillaries. Maybe not quite that high. It went above the graph. It's okay. And then back down again. Why does it go way up? Because we have so many capillaries. So even though they're thin, they split, and there's so many of them. It's like a river splitting into a whole bunch of separate rivers, that you're going to have a large area, even though they're very thin. And that kind of makes sense if I think about what those capillaries look like, those capillary beds, they spread out quite a bit. Because of that cross-sectional area, what is velocity going to look like? Sorry, let me go. Yeah, down here is velocity of blood flow. So what happens to velocity as you increase cross-sectional area? It's going to slow down. If you have more branches to branch into, the flow in each of those branches actually slows. So velocity of blood flow is going to start pretty high. That's close to the pump, right? We're pumping out, we have that pressure due to the pump of the heart is going to result in a high flow rate at that aorta, and then the veins close to, arteries close to the heart. A drop here and drop pretty darn low at the capillaries, pretty low velocity, but then we start to creep back up again. And that's largely because we're going from a high cross-sectional area back to low again. So as those branches recombine, velocity is going to increase. So like here, we're going from one single tube, the aorta. Let's say we split it. I'm not drawing accurate splits here, but I mean, there's a lot more splits in this in reality. Capillary beds, right, are crazy amounts. This is not how it looks biologically, but all these splits, and then these are going to start to join together again. And actually, I should have that in blue. As they join back together, and those join back with other ones. And this is simplified, obviously. Eventually, we become the vena cava. Because of that, this is explaining our cross-sectional area. This is also higher velocity, lower velocity, and then higher again. It doesn't ever reach the velocity it had at the heart because we're still pretty far away from that pump, right? There are some pumping type mechanisms I'll talk about in the veins as well that contribute to this, with getting the blood back to the heart, increasing that flow, that also contribute to this increase right here.